Okay, today we are going to do series. Last time was sequences, this is series. Those are always paired together. You always hear sequences and series. So I'll tell you what that means. Okay. Series is not what you think. Normally we say that's a number that's in a series, which means that it goes in a certain order. But in math, when you say series, that means that you are going to add up all the numbers that are in your lists. So a series is just a sum of a sequence. Okay. A lot of times it's not all of the numbers in the sequence, obviously, because they go on forever. And not very often do those end up adding up to just one certain number. So it's a sum of numbers that are in a sequence, but not all of the numbers more than when we try to add up all of them. So the sum of a sequence, but not all of it. So we call it a partial sum. All right. So we're going to do arithmetic series and geometric series today. I'll also show you what summation notation is for you to do that. But just we'll start out with arithmetic. We'll be able to develop the formula for arithmetic series pretty easily. Arithmetic. So just a recall from last time, arithmetic is when you add the same number or subtract the same number in between your terms. So I'll just do an example. Arithmetic series where we're going to add up our numbers. So if you've got the following numbers, we'll just do odds, 3, 5, 7, 9, and 11. So we're just doing 6 terms. They're going up by 2 each time. We start with the number 1. If we want to know what the series is, you can just say 1 plus 3 plus 5 plus 7 plus 9 plus 11. And get your answer. I think that answer would be 36. But there's also a quicker way to add up an arithmetic sequence or to have an arithmetic series. And this is a pretty clever way, and it always works with arithmetic sequences and series. If you pair together your numbers, 1 and 11, start with the beginning and do the end, and then move your way in. These sums are always going to be the same. 1 and 11 makes 12. 3 and 9 make 12. 5 and 7 make 12. You can't see the bottom of the 12. So we end up with 12 plus 12 plus 12, which is 36. It makes it a whole lot easier to add up these series rather than having to go through and type in 1 plus 3 plus 5 plus 7 plus 9 plus 11, which is fine if you have like 6 numbers, but if you had like 100 numbers in an arithmetic series, you don't want to have to do that. So what we can do is, using what we just figured out, we can make the equation that we use all the time for arithmetic series for us to do it. So in order to get 36, we pair together the first and the last, okay, and we know that's going to be the same every time that we do it. And then we had that number 3 times. So since we had 6 total numbers, if you're making them in a pair, there'll be 3 pairs. So if we can think about this, where n is going to stand for the number of terms we have. Okay, so we had 6 terms. If we cut that in half, we're going to have 3 pairs. So for our arithmetic series for our equation, we're going to use S for sum. N is our sum for however many terms we're using. Okay. The number of terms divided by 2. So we said that 6 divided by 2 because we're going to have 3 pairs of them. And then again, how did we get to number 12? We added the first term and the last term. But in this case, it is our 6th term. So it's our first term plus our last term, because we're looking for the sum of the 6th term. So everywhere we see an n, there's going to be a 6. The sum of the 6 terms is 6 divided by 2 times the first term plus the last term, which in this case is our 6th term. Okay, so just plugging those in. The 6th term, or the sum of the first 6 terms is 6 over 2 times 1 plus 11, and that will give us our arithmetic series, our sum of those first 6 terms. So we can use this for any arithmetic series if we're trying to figure out what the sum of a certain number of terms are. So that's our equation that we'll use for arithmetic. So we only have to know three things in order to plug that in. We have to know the first term, the last term, and how many terms we are looking at doing. Come on, pen, work. There we go. That's for arithmetic. Now I'll show you what's called summation notation. You might have seen this. I don't know if y'all did this last year or not, but it is a way for us to tell someone we're doing a series without writing out the numbers in the series, just using the explicit formula. So this is summation notation. One of the most fun things to say in math, just because it rhymes. So it looks a little crazy. It's not that bad. So we've got, this is a capital S in Greek. It's a sigma. So that tells us that we're going to have a sum. That's a sigma. Sometimes you'll have like the Greek mu and m, and that would mean you would multiply. We're not doing that right now. But so they use the Greek letters S and M to signify sum and multiplication. All right, they tell you which term number you're going to start with at the bottom. So this one we're going to start with our first term. And then they will tell you a number at the top, and that's how far they want you to go. That's how they want you to go from 1 to whatever this number is. So in our case, I'll just say that we might want to go to the 12th term. So this is where you start. This is where you stop. Okay, and then you'll also be given an equation here that tells you how are you going to get the numbers that are in your series and how are you going to evaluate that. So let's just do a pretty basic one. I'll do an arithmetic one. Remember, arithmetic are just linear functions, so everything's to the first power. So if I had something like 2n plus 3. So this is what it looks like. They tell you you're going to start by plugging in 1. You're going to stop when you get to 12, when you're plugging in 12. And since it has this, that means that we want to add up all 12 of those numbers that we would get. Okay, so you can kind of start out by seeing if I plug in 1, 2 times 1 is 2 plus 3, so that's 5. And it's the sum, so we're going to add them together. Now I'm going to plug in 2. 2 times 2 is 4 plus 3, that's 7. Okay, then I'll plug in 3, and it looks like I'm going up by 2 each time, 9. Dot, 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 dot. And then I'm going to see what my last number is, because I don't have to actually write them all out. All I need is my first, my last, and how many terms there are, and I can use my formula. So I'm going to plug in 12. 2 times 12 is 24, plus 3 is 27. Okay. So that's how you generate your series using your equation. You're just going to plug your numbers in, first term, second term, third term, fourth term, etc. But I don't ever, especially if there's 12, I'm not going to write all those out. I'll just use my equation. So my sum for my 12 terms, how many did we do? 12 over 2. The first term is 5. The last term is 27, which is going to be 6 times 32, sorry. 6 times 32, I just made this one up. So this looks like that's 180 plus 12, 192. All right, so that is your arithmetic series stuff, summation notation, and also if they give you the list of numbers out or tell you how many terms there are. So there's your arithmetic. Here's one I'm going to want you to do and answer it when I put the question up there. There's no way for me to type this stuff. I guess there is, but it'll probably take me a while to figure out. So I'm just going to write this question up here for your first one that I want you to do, and you just type your answer in. So here's your on your own number 1. Let's go. I'd like you to find the series represented by this summation notation. You're going from 1 to 10. And your equation is going to be 3n plus 1. Okay, so take a couple minutes, plug in some terms that you need to plug in, and then use your formula. So I'm not going to work it out for you. I'll just check it. I don't know if y'all can see when I grade these if they're correct or not. So someone let me know if you can. In the comments below, just kidding, there's no comments below. I'm no YouTube star. So, all right. So I'll check and see if y'all got that one. And now we're going to go on to our geometric series, which they're a little bit different just in the way that they are, because not every geometric series can be evaluated like if it goes on forever. So they're a little bit different. Geometric series. We're not going to establish the equation like we did for arithmetic series. There's not just quite a simple like pair these up and then multiply it by this number for that. So I'll just go ahead and give you the formula for your geometric series. So our sum, okay, it's going to be your first term times 1 minus your ratio to the number of terms divided by 1 minus your ratio again. So remember your ratio, that's like your base. That's what you're multiplying by each time. But when it shows up in an equation, that is your base for that. So 1 minus r to the n, or the first term times 1 minus r to the n over 1 minus r. So we'll just do a couple of these. We'll do one without summation notation and then with summation notation to try. So our first one, let's say I had 3 plus 6 plus 12 plus ... and they tell us that we want to do this for 8 terms. Okay, so for our geometric series, we have to know first term, ratio, and how many terms there are. Do we have that first term? They give that to us, obviously. We know how many terms there are. We just need to figure out what our ratio is. And this looks pretty easy. This is a times 2. So we just plug those in. Oh, there's my email. I'll plug it into my equation. Our sum for 8 terms in this geometric series is our first term times 1 minus 2 to the 8th divided by 1 minus 2. If you're doing this in the calculator and you don't have like the fraction tool, make sure that you put parentheses around the top and the bottom if you're just using the divide by. Fine. So I haven't done this one yet. I just made it up. So let me do that real quick. We've got 3 times 1 minus 2 to the 8th divided by 1 minus 2. And that is 765. Okay, so if you kept going till you got to the 8th term and then you added all those up together, you get 765. Okay, now we'll do a summation notation one. They don't have to use an N. You can use any other letter. Sometimes it's an I, sometimes it's a K. I'll do a K. So we'll start with our first term. Let's go to the 7th term. And for geometric, remember it looks like an exponential growth or decay. So let's say I started at 4. I'm going to go by half each time. And then when you see these always look like this, K minus 1, are the ones that you're going to do. You're going to have K minus 1 in the thing, just like your equation was when you were writing it for your series. All right, so now it looks a little different. We have to figure out the first term. We've got to figure out what the ratio is, so we need to know how many terms there are. So this is how many terms there are. So that is our N. Our ratio is here, okay? And our first term is always the number that's in front of the base. And so occasionally there won't be a number right there, and then you know your first term is 1 because there's an understood 1. But you can always just check and make sure. You can plug your numbers in. If I plug 1 in for K, 1 minus 1 is 0. Anything to the 0 power is 1. And 1 times 4 is 4. So our first term is 4. You can try the next one. Plug in 2. 2 minus 1 is 1. A half to the first is a half. 2 times a half, or 4 times a half is 2. So it looks like we're cutting in half each time. The next one would be 1, the next one would be a half, etc. But we can just look at these equations and see N is 7, the first term is 4, the ratio is 1/2, and we can plug it into our geometric series formula. So S sub 7 is first term for, oopsie, not a big parentheses. 1 minus, my ratio is 1/2 to the 7th over 1 minus 1/2. Plug that in. 4 times 1 minus, I'm going to do 0.5 just so I don't have dual fractions, to the 7th divided by 1 minus 0.5. And it says that our sum is 7.9375. Okay, so that makes sense because we started out with 4 and we were cutting it in half each time, so there's no way that we could get up to 8. We're going to get closer and closer to 8 as it goes along, but we'll see that in a second. Okay, so those are our arithmetic and geometric series that go to a certain point. So those were called finite geometric and arithmetic series. Sometimes we have infinite geometric series, so that means they go on forever. You're going to add up all the numbers, and there are 2 different types of infinite geometric series, and we'll look at those. So they fall into 2 categories, the ones that when you add up all the numbers forever and ever and ever and ever. The numbers can be getting, if your numbers are getting like super, super huge and you're adding big numbers and big numbers and big numbers over and over and over, you're never going to get to a specific answer. And if that happens, we say that the series diverges. So we can have divergent geometric series. So they can diverge, so they're going to diverge if your series or if your ratio is something that's growing. So you're going to diverge if your ratio is bigger than 1. So we do the absolute value of that because it could actually be positive or negative. It could still diverge. So if your ratio is bigger than 1, which means you have a growth function, if you add up all those numbers, it's never going to end. It's just going to get huge. Okay, so they diverge. So anytime you have a ratio bigger than 1, you're going to say it diverges. Okay, and it converges if it is less than 1. So it'll converge to a certain number. You're actually going to get an answer, even though you're adding together an infinite number of numbers. It's not going to get any bigger. Oh my gosh. My mother is calling me 14 times. Okay, I'm back. I don't know what I just said. So diverges is when your ratio is greater than 1. Converges is when it's less than 1. I just wanted to show you a picture of why that's actually the case. Like say our ratio was a half, because that's something that's less than 1, and we started out with the number 1. So we started at 1, and then we're cutting it in half every time, a half, and then a fourth, and then an eighth, and then a 16th. If we go on forever and ever and ever, you think, oh, I'm adding something, so my number is going to have to keep getting bigger, but it actually doesn't. So I can do this with a picture. If I have 1, so there's 1, and then I'm going to add a half to that, and then I'm going to add a fourth to that, then I'm going to add an eighth to that, and then a 16th, and then a 32nd, and 64th. You can see how it's going to get smaller and smaller and smaller, what we're adding. So even though we're adding numbers over and over and over again, in this series, we don't necessarily get to anything that's bigger than 2. So the largest number we're going to get super, super close to 2. We're not actually going to reach the number 2. So we say that this series would converge to 2. So that's just kind of why these numbers, even though it looks like, oh, I'm adding something, so it's going to have to get bigger, it's not going to sometimes reach a certain number. Like it does get bigger, but it doesn't go past a certain amount. So that's why we say it converges to a certain number. So one more quick question, a little OYO. We'll just do one. Does it diverge or converge? So that's what your question is going to be. So you'll answer converge or diverge. So here is our series. We'll go from 1 to infinity. These are the infinite kind. 5 times 1/3 to the n minus 1. So just tell me right now in the question, does it converge or diverge? So you'll just write that answer down. Okay. All right. And then we also want to figure out if it does converge. So if the ratio is less than 1, what does it converge to? So if you have a convergent series, we have a quick formula to tell what it converges to. So if you have a convergent geometric series, this is what you will get for your answer. So we figured it out that that one was going to go to 2, but just in case we can't visualize it or the numbers are a little bit weird, this is what it converges to. Okay, so it's going to be the first term over 1 minus the ratio. So that's what we are going to converge to. We can test it out with this one that we just saw. Our first term, sorry, scrolling. So if we want to try it with the one from above, our first term was 1. Then 1 minus, what's our ratio? It was 1/2. So 1 divided by 1 minus 1/2. We can evaluate that, and that's going to give us 2. So it would converge to 2. All right. So if the ratio is less than 1, first term, 1 minus the ratio, will tell you what the infinite geometric series converges to. So I'll give you one of those to try real quick and see if you can get it. So this is our third question. N equals 1. We're having an infinite geometric series. Let's say our first term was 7, and we're going to go by a 4th. There we go. To the n minus 1. So just tell me real quick what this series converges to. So I'm telling you it converges, our ratio is less than 1. You'll use this formula. First term divided by 1 minus the ratio for that. So try that question real quick. Write that down in your answer. And there we go. That's all for today with your arithmetic series, geometric series, and infinite geometric series. Sorry this took a little while, but there was a lot of stuff, a lot of formulas. Tomorrow or next time will be shorter for sure. All right, thank you very much, and good day.